One bolt of lightning lasts less than a second, yet it carries enough raw electrical energy to power an entire city for 60 seconds. How does something invisible, uncontrolled, and gone in a fraction of a blink contain that much force? Why can't we capture it? And what would happen to every electrical grid on Earth if we actually could? The answers involve numbers so extreme they sound fictional. Temperatures hotter than the surface of the sun. Speeds that approach the cosmic speed limit of the universe. Forces strong enough to turn ordinary beach sand into glass in milliseconds. You have seen lightning your entire life. You have never actually understood what it is. That changes right now. Let's start with the raw physics, because the numbers alone are enough to stop electrical engineers cold. A single lightning bolt carries approximately 1 billion volts of electrical potential. 1 billion volts. The standard household outlet in your wall delivers 120 volts. A lightning bolt carries over 8 million times that voltage in a single discharge, lasting less than a second. The peak current in an average lightning strike reaches 30,000 amperes. That's 30,000 amps, roughly 300 times the current flowing through a standard household circuit breaker running at full load. Enough current to vaporize a steel rod 2 centimeters thick instantly. The total usable energy in one average lightning bolt is approximately 250 kilowatt hours. That figure needs a comparison to land properly. 250 kilowatt hours is enough electricity to run a standard household refrigerator continuously for 6 full months, or power a 100-watt light bulb for nearly 3 years without a single interruption, from one bolt, gone in 0.2 seconds. The temperature inside a lightning channel reaches 30,000 Kelvin. 5 times hotter than the visible surface of the sun. The sun's photosphere sits at approximately 5778 Kelvin. Lightning exceeds that by a factor of 5 generated spontaneously in open air between a cloud and the ground in under a second. The bolt itself is astonishingly narrow. The actual conductive plasma channel is only 2 to 3 centimeters wide, roughly the diameter of a human thumb. That thumb-width channel carries enough instantaneous current to melt through solid copper wire instantly. Lightning's return stroke travels at speeds up to 270,000 kilometers per second. That is 90% of the speed of light. The visible flash you see completes its journey from ground to cloud in approximately 0.2 milliseconds. That is 200 microseconds. Less time than it takes a hummingbird to beat its wings a single time. The average lightning bolt discharges across a total duration of 0.2 seconds. Some bolts contain multiple return strokes, up to 19 separate discharges within a single visible flash, each separated by only 40 to 50 milliseconds of darkness. This is why some lightning appears to flicker. Earth experiences approximately 100 lightning strikes every single second. That is 8.6 million strikes every day. Over 3 billion bolts per year, hitting every continent, every ocean, every desert on the planet continuously around the clock without interruption. The total instantaneous power of all Earth's lightning combined reaches approximately 1 terawatt. 1 terawatt is roughly equal to the entire electrical generating capacity of the United States power grid running simultaneously at maximum output. All of it produced by water vapor, ice crystals, and atmospheric charge, for free every day, whether anyone is watching or not. So what actually creates a lightning bolt? The physics is stranger and more violent than most people expect. It starts with ice. Inside a thundercloud, ice crystals and supercooled water droplets collide violently in updrafts reaching speeds of 160 kilometers per hour, fast enough to lift a small car vertically off the ground. These high-speed collisions strip electrons from ice crystals, separating positive and negative electrical charges within the cloud. The bottom of the cloud accumulates negative charge. The ground beneath accumulates induced positive charge in response. Think of it like two terminals of a battery being slowly charged, except this battery is 10 kilometers tall and contains billions of tons of water. The voltage difference between cloud base and ground builds until it reaches approximately 300 million volts per meter of air. At that threshold, the air itself stops behaving as an insulator. It begins to ionize. Electrons are stripped from air molecules, creating a conductive plasma channel through what was previously empty atmosphere. This invisible channel is called the stepped leader. The stepped leader descends from the cloud base in discrete 50-meter segments. Each segment takes approximately 50 microseconds to form and extend. The entire stepped leader descent covers 10 kilometers of vertical distance in roughly 20 milliseconds, approximately the duration of a single human blink. Here is surprising fact number 1. Lightning does not simply strike downward from above. Simultaneously, the ground sends upward streamers, positive charge reaching upward from trees, buildings, antenna towers, and any elevated conductive object. These upward streamers are invisible. When a descending stepped leader and a rising upward streamer connect, the circuit closes. That connection point triggers the return stroke, the massive luminous discharge traveling upward from ground to cloud at 90% of the speed of light. You perceive the flash as traveling downward. In reality, the brightest, most energetic event travels upward. The stepped leader spent 20 milliseconds descending invisibly. The return stroke completes the same journey in 0.2 milliseconds, 100 times faster. Your eyes register only the brightest event in a sign direction based on where the flash first appeared visible. The entire perception is inverted. Surprising fact number 2. The thunder you hear is the sound of air expanding at supersonic velocity. The lightning channel heats surrounding air to 30,000 Kelvin in microseconds. That air expands outward at velocities exceeding 1,200 meters per second. The speed of sound at sea level is 343 meters per second. The expanding air moves at 3.5 times the speed of sound, generating a shockwave. That shockwave is thunder. The low rumbling that follows a close strike and persists for several seconds is not multiple thunderclaps. It is the same single bolt, with sound arriving from different points along a channel that may stretch 8 kilometers or more horizontally. The closest part of the bolt arrives first. The farthest part arrives last. One bolt, several seconds of rolling sound. Surprising fact number 3. Most lightning never touches the ground at all. Approximately 75% of all lightning discharges occur entirely within or between clouds, completely invisible from the surface. The cloud-to-ground strikes that humans observe, fear, and photograph represent only 25% of total global lightning activity. 3 out of every 4 bolts discharge entirely above your head, hidden behind cloud cover. Here is where the engineering question becomes genuinely difficult. If one bolt carries 250 kilowatt-hours of energy, why can we not capture it? The problem is not the quantity of energy, it is the speed of delivery. Those 250 kilowatt-hours arrive in 0.2 seconds. A standard home electrical panel accepts power at a continuous controlled rate of roughly 20 kilowatts maximum. Absorbing 250 kilowatt-hours in 0.2 seconds requires accepting power at an instantaneous rate of 4.5 gigawatts. 4.5 gigawatts. That is the combined full output of 4 large nuclear power plants, delivered simultaneously into a single point in 1/5 of a second. No capacitor, battery, or electrical storage system currently in existence can absorb energy at that delivery rate without immediately destroying itself. The fastest commercially available supercapacitors can absorb power at approximately 10 megawatts maximum. A lightning bolt delivers 450 times that rate. The storage system disintegrates before the bolt finishes discharging. The voltage mismatch creates an equally insurmountable barrier. At 1 billion volts, a lightning bolt instantly arcs through and destroys any conventional transformer before voltage step-down can begin. The world's most extreme high-voltage transmission lines, used to move power across continents, operate at 765,000 volts. Lightning carries 1,300 times that voltage. No transformer built today can bridge that gap without immediate catastrophic failure. Then there is the geographic unpredictability problem. Lightning strikes are effectively random at the scale of individual bolts. A single square kilometer of land receives on average only 1 to 6 lightning strikes per year, depending on geographic location. To capture enough energy to power even a modest city of 500,000 people, capture infrastructure would need to span thousands of square kilometers, all connected to storage systems capable of handling gigawatt-scale power spikes, all active during 0.2-second windows that cannot be reliably predicted more than minutes in advance. The world's largest operational battery storage facility, Moss Landing Energy Storage in California, holds approximately 3,000 megawatt-hours of capacity and cost over $1 billion to construct. One average lightning bolt would contribute 250 kilowatt-hours to that facility, filling 0.008% of its capacity. At commercial electricity prices, that energy is worth approximately 10 cents. The infrastructure cost of capturing one bolt reliably, hundreds of millions of dollars. The market value of what you captured, 10 cents. This is the fundamental economics of lightning energy harvesting. The most technically advanced approach to the problem involves triggered lightning, using small rockets trailing thin conductive wire to initiate a discharge from a storm cloud at a predetermined location. This technology was demonstrated successfully at the University of Florida in 2004, triggering 37 controlled bolts from a single storm system. Even with triggered lightning eliminating the geographic unpredictability problem, the absorption barrier remains completely unsolved. The bolt still arrives at 4.5 gigawatts in 0.2 seconds. Directing it to a specific location does not change how fast the energy arrives or how much storage technology can currently receive. Research at MIT and Stanford is developing graphene-based supercapacitors, storage layers just 1 atom thick, with theoretical charge acceptance rates approximately 100 times faster than current commercial supercapacitors. Even at 100 times improvement, the gap between what exists and what is needed to capture a single bolt remains a factor of 4.5. Lightning capture is not an engineering problem waiting for incremental improvement. It is a fundamental mismatch between the rate at which nature releases energy and the rate at which human technology can currently receive it. The energy is real, the gap is real, both remain true simultaneously. Now let's get into the facts most people have never encountered. First, lightning does not just heat air, it actively manufactures chemicals essential to life on Earth. Each bolt passing through the atmosphere forces nitrogen and oxygen molecules to combine under extreme heat and pressure, producing nitrogen oxides. Scientists calculate that lightning generates approximately 13 teragrams of nitrogen oxide annually across the globe. 13 teragrams is 13 trillion grams, produced entirely by atmospheric electricity at zero cost. These nitrogen oxides dissolve into rainwater and fall to Earth as a natural fertilizer, contributing meaningfully to the soil nitrogen cycle that supports plant growth worldwide. Without lightning, the nitrogen chemistry of Earth's soil would be fundamentally altered, with cascading effects across global agriculture that scientists have not fully quantified. Second, lightning creates glass. When a bolt strikes dry sand, the 30,000 Kelvin temperature fuses silica grains into irregular hollow glass tubes called fulgurites. Some fulgurites have been excavated stretching over 5 meters underground, longer than a full-size pickup truck, formed in less than a second from ordinary beach sand, preserved intact for thousands of years. Researchers have found fulgurites on every continent including Antarctica. Ancient civilizations who discovered them had no explanation for their existence and sometimes treated them as sacred objects. Third, for scale, consider the power density of a single bolt against a human engineering achievement. The 4.5 gigawatts delivered instantaneously by one average lightning strike equals the full power output of the Hoover Dam running continuously for approximately 4.5 hours, compressed into 0.2 seconds. The Hoover Dam required 5 years of construction, 21,000 workers, and 3.25 million cubic meters of concrete to build. Lightning replicates its multi-hour output 8.6 million times per day, using nothing but water vapor and atmospheric charge. No concrete, no workers, no construction time. Fourth, the odds of being struck by lightning in your lifetime in the United States are approximately 1 in 15,300. Your annual odds of being struck in any given year are 1 in 1,222,000. Your annual odds of dying in a car accident are approximately 1 in 8,000, over 150 times more statistically likely than being struck by lightning in the same year. Lightning dominates human fear response, completely disproportionate to its actual statistical risk. It is dramatic, sudden, and unpredictable, all features that trigger strong fear responses regardless of actual probability. Statistically, the drive to the stadium where you watch the storm is considerably more dangerous than the storm itself. Fifth, and here is the controversial part. A growing number of physicists and energy engineers argue that lightning energy capture is a scientific distraction that consumes research funding without meaningful energy potential. Here is the math behind that argument. The total energy contained in all of Earth's lightning combined, all 3 billion volts per year, equals approximately 750 terawatt-hours annually. Global electricity consumption is approximately 28,000 terawatt-hours per year. Even capturing 100% of all lightning on Earth with perfect efficiency and zero losses would supply less than 3% of current global electricity demand. Critics argue the engineering talent and funding currently directed at lightning research would produce thousands of times more usable energy per dollar if redirected towards solar, wind, or advanced fission technology. Supporters counter that triggered lightning research produces scientific value in atmospheric modeling, climate science, and telecommunications interference research that justifies the investment entirely independent of energy yield. Both positions are financially coherent. What neither disputes, lightning remains the most extreme natural electrical event that humans can directly observe, measure, and interact with, and understanding it precisely has value that extends far beyond whatever electricity it might someday provide. So here is what you actually understood today, stated plainly. One lightning bolt, 1 billion volts, 30,000 Kelvin, 90% of the speed of light, 250 kilowatt-hours of energy delivered in 0.2 seconds at a rate equivalent to 4 nuclear power plants firing simultaneously into a single point. We cannot capture it, not because the energy does not exist, but because it arrives faster than anything we have built can receive. 8.6 million bolts discharge every day across this planet. Each one manufactures atmospheric fertilizer, sometimes creates underground glass that survives for millennia, and releases energy equivalent to hours of output from a major dam, in less time than a camera shutter opens and closes. The gap between what lightning is and what we can currently do with it is one of the clearest measurements of where human engineering actually stands against the physics of the natural world. We understand lightning almost completely. We can predict storm systems hours in advance. We can trigger individual bolts using rockets and conductive wire. We can measure the return stroke to microsecond precision using high-speed cameras and electromagnetic sensors. We just cannot hold it. Here is the question worth sitting with. If a bolt of lightning contains enough energy to power a city, and we cannot capture it with the most advanced electrical storage technology currently in existence. What does that tell us about the true gap between human engineering capability and the raw energy scales of the planet we live on? Maybe the most useful answer is the most honest one. The gap is real. The gap is enormous, and closing it, even partially, will require engineering breakthroughs that do not yet exist. That is not a failure. That is where every meaningful engineering problem actually lives, in the space between what is understood and what is possible. If this changed how you see the world, hit subscribe. We uncover the truth behind things you thought you already knew. Somewhere above you right now, a thundercloud is building charge. Electrons are separating from ice crystals at 160 kilometers per hour. A stepped leader is forming invisibly, descending 50 meters at a time through ionized air toward the ground beneath it. In 0.2 seconds, it will release more instantaneous power than 4 nuclear reactors running simultaneously. And it will be completely gone before you hear the thunder arrive.